All right, hello Prairie View. We had a little bit another problem. For some reason when we're connecting over, we seem to be having trouble on Fridays. I don't know why. My intention today is to just keep working through the rest of those test your knowledge problems. So I want to go through them, make sure that we're good, and then maybe we'll get through, maybe we won't get through relatively today, but we certainly will be done by Monday. I did finish your homework assignment. I will be shipping it out this afternoon. You have 1 week, so it's due a week from today. You can work in groups of 2, or you can work in groups of 3, or you can work by yourself if you're a loner. There is something to be said for working together. You learn something from your peers, at least as much as you learn from your teachers and your mentors. But on the other hand, if there's too many people, then usually some people are not doing anything. And then that shows up on exams. All right, so make some sort of arrangement. You can scan it. You can fax it to me. If you do scan it, look at it. Look at the file after you're done, because obviously I'm grading what I see. So if you write really light and it doesn't come through the scan, I won't be able to see it. So check your work. Also try to number every page and put your initials on it. That way if the pages get sorted or separated, I can actually put it back and make sure that you get credit for all your work. Okay? With that, first I want to test your knowledge problems, and I've kind of actually worked it out. Just kind of save us a little time. Let me bring in, and if I'm not in far enough, or if the stuff is running off your screen on the remote site, let me know. Because what I see on my screen appears to be a larger amount of material than what I see in the video when I look at it, and therefore I don't know what you're seeing. So for instance, I can see right now all the way to the end of the page, but I'm noticing sometimes when I can do that, when I'm looking behind me, that like the last line is cut off on the video, and I'm not sure at Prairie View whether you're seeing it the same thing I am or not. Okay?
It's cut off.
Can you see the whole page?
No, we cannot see the whole page. The bottom part is cut off.
See, I can. Okay, so tell me when you can see the whole page.
Okay.
All right. So, see, for me, that looks like it's only about 80% of the screen. So there's obviously a difference between what you're viewing and what I am. All right, so here's the problem. It says, suppose an observer O determines that 2 events are separated by 3.6 10 to the 8th meters, and that they occur 2 seconds apart. What is the proper time interval between the occurrences of these 2 events? Now, O is not the proper time observer. You're being asked to find another frame. Here's one of the things that's different. They did not tell you what the speed of the other observer's frame is. The only thing they told you was they were a proper time interval measurer. So the first thing I did here is I identified these 2 things. That and that, distance and time, and I wrote them as delta t and delta x. The second key thing is, what does it mean to be the proper time interval measurer? It means that the clock or the event does not change location during the measurement. So its initial x and its final x has to be the same. Another way, delta x has to be 0. That's what this statement told me. Without that, I'm going to be totally stumped. All right, so that's a very important on these problems. The key thing is to know that delta x prime has to be set equal to 0. So that's the proper time condition. Delta x prime is 0 meters. Okay? Once you have that, then they're asking you to find delta t prime. You have the Lorentz equations. I don't expect you to memorize the Lorentz equations. I will give you the equations, but I expect you to know how to use them. Okay? So, the first thing I'm going to need in order to calculate delta t prime down here is, yes, I have delta t, I have delta x, but I do not know v, the relative motion between the observers, and without it, I cannot calculate gamma. So I cannot just jump to this formula and work the problem. I have to first find v, and I do that by looking at the position equation of the Lorentz transformation. Delta x prime is 0. Therefore, this term right in here must be 0. So I solve that for v. Well, if you do that, you get v is delta x over delta t, distance over time. So that's not any amazing thing. I put 3.6 10 to the 8 meters over 2 seconds. Now, that'll get you something in meters per second, but remember, we want to measure speed always in terms of c. So what I did is I multiply this by 1. c on top and 3 times 10 to the 8 meters per second on bottom. That's still 1. This will enable me to knock the 10 to the 8 out. 3.6 divided by 2 is 1.8. And 1.8 divided by 3 is 0.6. So it's 0.6c. And now I don't have to work with those big numbers anymore. All right? Just a trick of the trade. Now that I know the speed, that the proper observer is moving at 6/10 the speed of light compared to observer O, now I can go ahead and apply the equation of the Lorentz transformation to this problem. So I find gamma, which is 1 over the square root of 1 minus 0.6c over c, so that's just the beta, 0.6 squared, and I get 1.25. So there's a 25% correction due to gamma. Yeah?
What is moving? What is v?
V is the relative motion between the two observers.
So it's the observer.
Well,
between the observers.
You choose which one you want, and the other one's moving at 0.6c.
And we chose the proper time interval to be the one.
It's a matter of which one you choose. All right? So you either say, hey, proper time measure is moving at 0.6c with respect to me, and I'm Mr. O, or you can be the proper time measure and say, no, I'm at rest, and observer O is moving at 0.6c. Only relative motion has me. So once you take and you have V, then you can put that V in there, and once you have gamma, which you needed V to calculate, you can put that in there. Again, you're going to have this kind of unit thing which can help. You got the 2 seconds, that's not a problem. You have the 0.6c, that's not. That'll help you cancel this c here. But this delta x, it's not in c meters or something like that. Okay, so what you need to do here is 3.6 10 to the 8 meters. Go ahead and divide that by 3 times 10 to the 8 meters per second. Put in the value of c here. That'll kill the 10 to the 8, it'll kill the meters, and it'll bring seconds up on top. So if you look at that, you got 0.6, 3 over 3.6 is 1.2. So you have 0.6 times 1.2, and you subtract that from 2 seconds. And then you multiply the whole thing by 1.25. You do that, you get 1.6 seconds. Remember, the proper time measure always measures the smallest time. So you better get a number less than 2.
Excuse me, sir.
So always measure less than any other front. So this person did not see it at the same time. I'm sorry?
One thing is kind of throwing me off. Looking at the top, it seems like the way you written it, observer O is the proper time and proper distance measure. But I thought that's not possible.
Just a second, I'm trying to turn up to see if I can hear. I can't quite hear you. Okay, try again.
Can you hear me now?
Yeah, much better. Okay.
Good. Can you slide your paper up a little bit?
This one?
To the top? Yes, it seems like you have the observer O as having the proper time and proper distance.
No, in the general Lorentz transformation equation, when you're writing them, there isn't written a TO or a TP. They're just either primed or unprimed. Okay? So I do not know that this is a proper length. I do know that that is not a proper time. I know it is not a proper time because delta x is not 0. In order to be a proper time, or a proper time measurement, the clock has to be at the same location when all time measurements are made. Remember our little race the other day. So there's my clock. That was at the origin. And when he got to the end of the race, some later time, he was still at the origin. So delta x didn't change. And that's why he was the proper time measure. So the guy over here, the clock moved along x. So they were not a proper time measure. This one has a delta x. It cannot be a proper time measure.
Okay, I understand now.
But that does not mean, that does not imply that he is the proper length measure. I don't know. I do not know if he was at rest with respect to some ruler. These are more complicated problems than just measuring the length of an object. Okay, these are ones where you have two events that occur at different seconds. These are things that occur where you have objects that occur at two different points in space. They're not just measuring the length of a distance or the length of an object. And because of that, you have to apply the entire Lorentz transformation equations. You're not just applying those special case problems where you use L equal L naught over gamma. Those were designed where either delta T was 0, which will get you the L equal L naught over gamma, or they were if you had delta X equals 0, and you got the other. These could be places where the person is neither the measure of time nor the proper measure of length. You never can be both, but you may be neither. In this problem, I don't know. What I do know is they do make me find the second observer and make him the proper time person. Because they told me to. And to do that, you have to make the prime observer's distance measurement 0. Much more complicated problem than the length problems. All right, got to use the full. Something else you'll notice in the notes, if I can find them, the ones I gave you just have T and X. If I can. These equate. These equations, for instance, that I'm using, this one and this one, you don't see a delta. That's okay. You can take T1 and T2 and subtract them. So you can just put deltas in these equations. So you can rewrite this guy. Putting in these deltas. You don't have to find T2 prime and T1 prime and subtract the two. That's what I'm doing. I'm finding T final with an equation. I'm finding T initial. I'm subtracting. When I do that, I get T2 minus T1. And this one, prime. And this one, I get T2 minus T1. I get X2 minus X1. It's just the same as putting the deltas in. But these are more complicated versions of the equations that work in all situations, whereas the ones where you have the length type problems, like the Fitzgeralds, if you look the way this was proved we found x2 minus x1, and we had an x2 prime minus x1 prime using the Lorentz equations. There's some other stuff over here. We made that go away. We made that go away by saying delta t was 0. That's how we get to this equation. So this equation only works if delta t was 0. It's not a universal equation like the Lorentz equations were. And if delta t is 0, you're a proper length measurer. All right? Delta t was not 0 in my problem. It's not 0. This is not a proper length. This was not 0. This is not a proper time. This observer is neither a proper length nor a proper time measure. The Lorentz equations are more general than the length, contraction, or the time dilation. They're more complicated too. If you can do it without doing the full-blown stuff, great. But when you start talking about just events, not measuring the width of something or the time of a race, then you're going to need the full-blown stuff. And that's why these were later in the homework examples. They're more complicated. Other questions? Important stuff, because these are the more difficult ones to be able to work. All right? The main thing is to be able to figure out this statement. These guys, proper time or proper length, mean you're going to set something to 0. If it's time, then the length has to go to 0. If it's length, then the time, delta t, has to go to 0. And you use that to solve for the speed of the frame. Easier ones are they give you the speed of the frame and they tell you it's a proper measure. Then you get to bypass this sort of stuff. And life is much nicer. But you're not guaranteed to have that. Okay? All right, let's look at another problem. Next one in that set of homework type stuff. Ask you to do some things, again, about simultaneity. And the intertwining of space and time. So the next one said this. An observer O notes 2 events. Again, bam, bam, maybe 2 explosions. And he notes they're not at the same place in space. And they're not at the same time. They're separated by 600 meters. Maybe there's 2 explosions from 2 bombs. Or maybe it's 2 balloons. Or a baseball hit one place and something else. And they occur 800 nanoseconds apart. In fact, what they might be is 2 detectors. So you get a click when a particular particle from some nuclear reaction hits them. Okay? How fast must an observer O prime be moving relative to O if he sees them simultaneously? Click. So again, we don't know V, but we know something about it. We know that the time between the clicks is 0. So delta x is 600 meters. I'm going to call that the unprimed observer. Delta t is 800 nanoseconds. Again, I'm calling that the unprimed time. Delta t prime, you told me you wanted it to be simultaneous. That implies this. If the time between the event as measured by that observer is 0. Notice they do not agree on simultaneity. This one agrees 2 things happen at the same time. This agrees that it's 800 nanoseconds. So you can have something like, and here's a detector. Here's another detector. And there's some sort of particle. There's some sort of particle going like this. And the one observer sees this, say, at 0 and this at 600 meters. And maybe he hears this click, and then 800 nanoseconds later, that click. And to another person who is moving relative to the first, he sees them at some different distance, and he sees them happening simultaneously.
Does the delta t prime equal 0 correlate to some proper observation in the same way that delta x?
Well, you could say that it's going to represent back to a proper length between the two.
Yeah.
But we don't really care about that so much in this problem. It's not what's asked.
That's just
Okay, just curiosity, the answer be true. So this case, it's not too hard. You just put the straight Lorentz equation in. You know that. It's 0. You know this. You know this. You're looking for V. So if we go and just plug and chug, move this guy to that side. So I kind of skipped a step. We can cancel those gammas. We don't have to worry about them. Gamma can never be 0. It's got to be 1 or greater. And then that gives you this equation here. If I did it right. I go ahead and solve for V. So I've got c squared delta t over delta x. Leave the c alone, at least one of them, if you want the speed in terms of c. Take the other one and write it out. 3 times 10 to the 8 meters per second. You got 800 nanoseconds. That's 80 times 10 to the minus 8 seconds. The 10 to the minus 8 and the 10 to the 8 will cancel, so that's why I chose that. Makes it nice to kill those exponents. 600 meters in the bottom. So I've got 3 times 80, which is 2400, divided by 600, 0.46. The problem is almost always making sure you're careful and making sure you understand what they're telling you in the problem. Proper length, proper time, simultaneity. Know what the terms mean. You can handle relativity. Don't know what the terms is and try to wing it off your head, and you'll get yourself in trouble. Questions? Nobody here? Questions or grade you?
No, sir.
All right, then we should be good to go. Those are a little harder than those length and time guys, okay? We said some things in the discussion. There's a discussion about the fact that we mostly talked about length and time and talked about mechanics. But this idea of relativity and relative motion goes beyond that. There is no experiment, not just mechanics experiments, no electronic experiment, no electricity experiment, no solid state physics experiment, no physics of any sort that can determine absolute motion. So let's talk about some things that Einstein knew. He knew, for instance, the Doppler effect. The idea that if you send, for instance, a sound wave and you're going along and you have a moving source like an engine on NASCAR or a guy playing a horn on a train, that you hear a different pitch, whether it's coming towards you or away. He also knew that if you move toward the sound, you hear a different pitch. He also knew that you can detect who's moving. Now, how could that be? Because in the case of sound, there is a medium. And when you say moving, you have it with respect to. It's with respect to the medium, the air. So you're talking about, is the source moving with respect to the air? Is the observer moving with respect to the air? But in the case of light, there's no ether. There is no medium. There should be no way to detect in the formula which one is doing the moving. And so he had to go through and show that relativity was consistent for the Doppler shift for light. And he did. So to show you, if you didn't really catch that in physics 1 or 2, really physics 1, I gave you, besides deriving the formulas, a couple of problems that show you that for sounds you can detect who's the person moving with respect to the air. So the first problem has a 200 hertz wave, and the wave is traveling toward you, the observer, and it's traveling at 50 meters per second. And I say it's a moving source because it is moving towards you through the air. The formula for that, which I derived, showing you how and why that comes about, is that the frequency you would measure is equal to the frequency it emits times its relative speed toward you, v over v minus u. So in this case, the wave speed is 100 meters per second. That's the v. The source speed, which is the u, is 50 meters per second. You just plug in the formula. 200 hertz, v is 100 meters per second. 100 minus 50 is 50 meters per second. You hear 400 hertz. You hear a higher frequency. And that's what you hear in NASCAR when the thing goes, the oom is when it starts getting longer, is when it passes you. You hear the frequency go up. And NASCAR, the engine is what's moving through the air, and the engine is what's making the pitch. And so you hear the pitch go up in frequency. In a sonogram, if you apply this type of thing, for instance, to measure the relative motion of blood in a baby's heart, you have a little bit more complicated problem, because this would be a raise in the frequency when it gets to the blood, but your sensor is back here, so it then absorbs it and re-admits it back. So you actually have a combination. You have two parts. You have this part, and then you have the next part. The same is also true for a bat. He shoots out, the sound hits a tree, so it goes up in frequency going to the tree, but then the tree then acts as the source and shoots it back, and in that case, the source is stationary, and the bat, which is the observer, is moving. So it's a combination problem. You can look that back up in your freshman physics book. Okay? Let me look at the second part, the moving observer. If you did the same problem, but this time the source is stationary with respect to the air, and the observer moves toward it, that is, the car is running its engine, and you run toward the car, and you could run fast enough, you would hear a frequency go up as well. All the things are the same. There's the u, that's your relative speed. There's the speed of the wave. And I kept the same frequency. But the formula is different. It has a different form. It's not covariant. Right? It's f prime is f, v plus u over v. So it's up on the numerator this time. And I get 200 hertz. 100 plus 50 is 150. Divided by 100, I get 300 hertz. So if you're moving toward the car, you hear 300 hertz. If the car's moving toward you, you hear 400 hertz. By the difference in frequency, I can tell who is moving with respect to the air. So the point is, it doesn't violate the laws of physics of relativity. It's a relative motion with respect to the air. There's a frame, a medium through which it goes. Einstein wanted to get around that whole issue and talk about, for instance, light emitted from an atom. He wasn't thinking of atoms at the time. The light emitted, and what would happen to light if it's being looked at in different reference frames. Now, I gave you a problem on that particular stuff. We'll see if I can find where that problem is. And there'll be one in your homework like this. It says you have a relativistic Doppler shift causes the light from a distant galaxy to be blue shifted by 5%. By blue shifted, that means it's going to go up or down in frequency. What does that mean about wavelength?
It's going to go down way.
I'm sorry?
It's going to go down in wavelength.
It's going to go down. right? So you can do it either way. In this particular question, they want you to make the frequency go up 5%, and they want to know if you could measure that. Could you tell me the speed of the galaxy relative to the Earth? Now, this is a cool thing to be able to be done. We're going to find out later, or maybe you already know, when you look at a gas, for instance, it can have lines. If you look at it through a prism, and those lines can be different colors. And they act like fingerprints. Likewise, if you shine white light through a gas, at the same wavelengths as these colored lines would be, there'll be dark lines called absorption lines. And you can measure those. And you can use that as a way of telling what's there. After all, how do we know what's the sun's made of? Not like the Aggies. We're not going at night. Okay? We know that by looking at the spectral lines. And in fact, helium was found in the sun long before it was found on this planet. Right? But these lines we find can be shifted. And we can use that shift as a way to tell us the relative speed of the thing that's emitting it. They're going to be close to where the lines are, so we can identify the elements. And if we know what the elements are on this Earth at rest with respect to us, then we can tell the relative motion using this technique. So, in this case, it says it's 5%. You're going to need the Doppler shift formula, which I worked out in your notes. And it says that F prime is F times the square root of C plus V over C minus V. This is if you're getting it blue shifted. F prime over F is going to be 5% more, so it's going to be 1.05. And that's the square root of C plus V over C minus V. Now, you can do what you want. You could factor a square root of C out of the top and bottom if you want. So if you prefer, you could write this as 1 plus beta over 1 minus beta. And you could solve this for beta. I don't care. It's up to you how you want to do it. Now, since you got a square root here, it'd be a good idea to square both sides. That would give you 1 plus beta, 1 minus beta. So 1 minus beta times 1.05 squared would have to equal 1 plus beta. And really, everything after this now, I've done physics. It's just algebra, okay? So I've got this term times 1, that's 1.05 squared. I have minus beta times 1.05 squared. I have 1. I have beta. I want to get all the betas on one side. I want to get everything else on the other side. That took care of that term and that term there. And on the other side, I have beta, and I have 1 plus 1.05 squared. So beta is 1.05 squared minus 1 over 1 plus 1.05 squared. And that is B over C. So find this value, multiply by C, and that's your V, which is what you were asked for. If you do that, assuming that I did it right, you get an answer like that. Sometimes people will ask you how much something differs from the speed of light, depending on your problem. And in fact, you can even do it up here. You could say, well, yeah, I could do this, and I could do all these steps. But you could have also, if it's small, relatively small, then you could have done a binomial expansion of that problem and saved yourself a lot of these square roots in algebra, and you would still got a pretty decent approximation. All right? And then you don't have any square roots and such in the problem. And in fact, if you were to go find a solution manual for this particular book where this problem came from, he doesn't go through all these steps. He applies the binomial approximation and works it out in like one line. Questions about how to do a problem like this? Pretty much straightforward. If you have it redshifted, it gets flipped. There is no discussion in the formula about who is doing the movement. It is relative motion between the two observers. All right. All right. You'll have some sort of galaxy problem. I will give you some problem. What I might do that's different is I might do, and I don't remember, depends on the book, but you could get a wavelength shift instead of a frequency shift. Remember that you've always got the fact that C is equal to F times lambda, which means it's also equal to F prime lambda prime. That's the statement that for any wave, the velocity of the wave is the frequency times the wavelength. The only thing that you know different about light is that light's speed in a vacuum you know. A water wave or something else you wouldn't. A sound wave you wouldn't. You'd have to know that. But in the case of light, you happen to know this side is C. That's a universal statement of a wave, and it's basically a statement that its distance over time is velocity. That's distance, the wavelength travels, 1 over the time for a wave to go through a wavelength. It's called the frequency. So this is basically lambda over t, which is distance over time. If you don't remember that from Physics 1, go back to Mechanical Universe or go look in the notes from Lewin at MIT and make sure that you could reproduce that off your head. All right. Any questions about this one? Not here. Preview. Any questions about relativistic Doppler shift problem?
No
You
question.
good?
No questions, he said.
Okay. All right. With that, let's move on to other things. So, Einstein looked at all the different parts of physics. That's what he basically did. He took the two assumptions. The speed of light is the same to all observers, and you cannot detect anything but relative motion. Put another way, the laws of physics are the same in all frames that are moving at constant velocity in a straight line with respect to each other. Nothing else. And then he said, with that and nothing else, let me go back, let's go pick up Holiday and Resnick, and let me reproduce the whole book. Let me go and look at things like the work energy theorem. The work energy theorem, we talk about work done by the net external force, which comes out of Newton's second law. Is Newton's second law true? We talk about collisions, and collisions conserve linear momentum. Are linear momentums conserving collisions? What we found is that if you define the momentum in a particular way, the way we did in regular physics, it's not. So he looked at collisions in different frames, and he found things like this. Again, it's in your notes. There's no need to be writing this right now. If you were talking about momentum being the mass that we've always talked about, the intrinsic stuff in our body, our desire to go in a straight line at constant speed, and if you're looking at the derivative of the position of the particle seen by Tom to the time seen by Tom, that quantity was not conserved. What was conserved was if this thing happened to be the proper time. But that may not be the same as this. Well, again, we can go and do some fun stuff. Nobody said we can't do other stuff like the chain rule. And if we do that, then now I've not done anything, I haven't changed it, but I've changed its meaning mathematically, where I've got this mass we always talked about, and now this is the position seen by Tom and the time seen by Tom, so that's my old velocity. But now I've got this thing out of the chain rule here, which leads to gamma. Now you get a choice here. You can just interpret this as gamma m naught b. Oops. Well, are you guys still there, preview? I see you, but I don't see my screen anymore.
Your screen's up there.
It's up there. See it?
Okay. So you can look at this in a couple of ways. And Einstein would have said this. He says mass really has no meaning except in a frame in which you measure it with respect to rest of yourself. That is, you take and you put it on a scale and you measure it, and that's all it is. I won't get into the finer thoughts of, and it's not my specialty, I'm sure there are many people much better than I am at it, of whether or not this is M naught, or whether you want to call this M. I'm going to call that M. And I'm going to talk about it. Yeah, about 6 minutes or so.
Hold on a second, I'm gonna have to shut it down.
All right, we're on a hold. We have inertia.
Yeah, maybe I missed something.
Hey.
All right, so I got everybody back. So my point is that Einstein preferred to be M naught and V and just have this gamma. I'm going to prefer, because I think it's easier for undergraduates, to just consider calling that in. When it's done, it's called a relativistic mass. So that the mass changes of an object based upon its reference frame. All right? So if I see an object moving, it doesn't just go up as M naught V. It goes by gamma M naught V. And I'm going to treat that, because it's going to be harder to deflect with a force, just as if it's a bigger object. It's going to behave in momentum way it's a bigger object. If it collides, I'm going to just treat that as if it's mass. But it's not intrinsic anymore. It's frame dependent. If it's not constant, you have some other things that show up. For instance, when you do the work energy theorem, and you integrate the work network, it's the work by the net force, like I did in Physics 1. When you do that, and you replace this by dp dt, that M naught is not constant. You cannot pull it outside like you did in relativity. And that's where the 1/2 mv squared of kinetic energy came from. So you cannot use the formula. Or equivalently, that. Do not do that. That formula will not work in this section. It is a classical formula. You cannot just put in the new M. It will not work. It's derived assuming the M was constant and pulled outside the interval. Right? Cannot work. Short of that, though, when you write F equal dp dt, that's true. As long as you use the right P. And the correct P is that. All the other things about physics that we learned before, we can use and interpret them, provided we use the right M. It's not surprising you don't get the right answer if you don't use the right math. Okay? So, while I understand the finer points of Einstein's argument about relativity, for an undergraduate, in order to be successful and move on with your classwork, till you get a lot more experience, treating that as if it is just like any other inertia, it is a mass, makes good sense. You'll have more success that way. So that's the way my notes do it. That's the way I'm going to do it. With that, I had a problem that talked about mass to kind of finish off the day. It says, what is the speed of an object whose mass is 3 times its rest mass? So you have that. So you're just trying to find beta. It's a simple problem. Square both sides. 9. Nine minus 9 beta squared will be 1. 9 beta squared will be 9 minus 1. Beta squared will be 8/9. V will be the square root of 8/9 C. So, length changes, time changes, mass changes. An interesting question is, what the hell is going on with the mass? I mean, what does it tell you? What's going on with the mass is that the increase in mass is an increase in energy. And the increase in energy is kinetic energy. So kinetic energy, this. That's the correct formula. It's a change in mass times c squared. Go through that section in the next section. Look at momentum, try to solve problems classically and relativistically. Look at energy. Be aware you can only use 1/mv squared or p squared over 2m in classical physics below a tenth of the speed of light. And by the way, you will find p squared over 2m is much better for k classically than 1/mv squared. It connects to quantum mechanics. Besides that, when these things get close, start moving up, p is the easier thing to measure than is v. V is very big. P is often not so big. It's an easier thing to measure. So get used to thinking more in terms of this, and you will find this one is not so useful. Both of those are classical. So you use this a lot in Physics 1. That one you'll use a lot more even in classical physics and upper level. All right, you guys have a good weekend.